Good afternoon, madam. Today, we would like to present about topic 8 as virtual memory. Virtual memory will include first in, first out, FIFO, and least recently used, LRU. I am Sharon Tianzixuan, and my another group members are Kelvin Kekaisun and Lim Chaoyuan, and we are from D1314 group. I would like to present about first in, first out from topic 8 as virtual memory. This will consider the following page reference string. Assuming a paging scheme with 4 frames is initially empty. Trace the allocation of pages to frames using 1, 2, 3, 4, 6, 1, 5, 6, 7, 1, 2, 3, 2, 5, and 1. Now we start to solve the question by using first in, first out. First in, first out is to replace the page that has been in memory the longest time. Then we have 4 frames, so for each frame we can insert one page. We insert the first page as 1 into the first frame. Then the highlight is the page fault. Page fault is the page that only appears for the first time. Then the number of 2 we just bring to the second frame. Then the number of 3 we also bring to the third frame. Then the number of 4 we just bring to the fourth frame. Then the number of 6 is not available in main memory and also not have free frame to insert. So we just using first in first out to replace the others page. We can see 1, 2, 3, 4 and 1 is the others page. Then we replace it as 6 in page 1 and page 4. Then it will become 6, 2, 3, 4. Then 1 also not available in main memory and then the number of 6, 2, 3, 4. 2 is the others memory, so we replace to 1 and 1 will become page 4 as the 6, 1, 3, 4. Then next is 5. Then we can see 5 is not in main memory, so 6, 1, 3, 4. 3 is the others memory, so we replace it to 5 and be page 4 and will become 6, 1, 5, 4. Next, 6 already in main memory, so we call this as the page hit. We do not need to replace any pages, just remain the pages. Next, for number of 7 is not in main memory, so we can see 6, 1, 5, 4. 4 is the others memory, so we just replace it to 7. 7 will be page 4 and will become 6, 1, 5, 7. Next, 1 is already in main memory, so we just remain the page. Then next, for the number of 2, 2 are not in main memory, so we can see 6, 1, 5, 7. 6 is the others memory, so we replace it to 2 and 2 will be page 4 and become 2, 1, 5, 7. Next, number of 3 are not in main memory, so we can see 2, 1, 5, 7. 1 will be the others memory, so we just replace it to 3 and 3 will be page 4 and become 2, 3, 5, 7. Next, 2 are already in main memory, so we just remain the page. Next, 5 also already in main memory, so we just remain the page. No need to replace any pages. Next, 1 are not main memory, so we see 2, 3, 5, 7 as 5 is the others page, so we replace it to 1 and 1 will be page hit and become 2, 3, 1, 7. And so the highlight, we calculate it as page fault. Total page fault is 11. That's all from me. Thank you.
Hi, lecturer. My name is Kevin Kekaisun. Today, I will be presenting about the least recently used LRU page replacement algorithm in the context of an operating system memory management. So, what is the meaning of LRU? The LRU is algorithm is mean a command page replacement strategy that remove the page least recently used when a new page need to be loaded. but the memory is full. So the assertion here is that patch used recently will likely be used again soon, while oldest ones are least likely to be needed immediately. So how LRU works? Let's look uh, let's look at the question. Consider the following patch reference rate. He have give the number 1, 2, 3, 4, 6, 1, 5, 6, 7, 1, 2, 3, 2, 5, 1. So assuming a paging scatter with 4 friends, it means that uh, it can hold 4 patches for a time. So uh, trace the allocation for patch for friend using. So uh, initially all friends are empty like this showing now. So as we process each patch in the reference tree, we either load it into memory or use the patch if it's already in memory. So if the memory is full, we replace the patch that has not been used for the longest time. So here is the table showing the friends allocated process. So in the beginning, patch 1, 2, 3, and 4 loaded into the empty threads. So 1 and then 2, 3, and 4. So when the patch 6 and here 6 is requested, the oldest patch will be 1. Why? We look at here. The 4 is uh, the first new has been used, and the 3 is the second new, and the 2 is the third new. So the 1 will be the older uh, older patch already. So we need to change it to be 6 become to 1. So it will be 6, 2, 3, 4. So let's continue. Uh, the next one is the requested. So we need to check back who is the older page. So 6 is the new one, and the 4 is the second new one, the page, and then 3 is third new, and 2 it will be the least recently used. So we want to change the 1 become to 2 lah. 6, 1, 3, 4. So the algorithm continue like this. For instance, when patch is 5, 5 is requested, the patch 3 get replacement because it has not been used for a while. So 6, 1, 5, 4. And then let's change to another patch. So next, the requested is 6. So if the number is sent, we no need to change anything. So it will be 6154. And then let's move to the next. The new one patch 7 is requested. So the oldest patch we need to find. So 6 is the new one, and then 5 is second new, and 1 is third new, and then 6 we have to at here 6 we have used already at here. So the 4 uh, will be the least recently oldest. So we need to change 4 became to the 7 like this. 6157. So next, uh, the patch 1 is requested, but 1 is have at the patch already. So we no need change anything. So 6157. Okay, let's move to another page. another patch 2 is requested. So now we need to change that. So we want to check back for 1. 1 is the uh, news users, and 7 is second, 6 is third, and 5 will be the least listening use. So we need to uh, let the 5 become to 2. So 6127. So let's move on. Now the algorithm continue like this. For instance, when page 3 is requested, page 3 sorry, page page 6 gets the replacement because it has not been used for a while. So it will be 3127. And then let's move on. Now is 2 is requested, but we have 2 already at here. So we no need to change anything. So we uh, copy that 3127, and let's go move on. Uh, Now it's request the file. So uh, when the page file is requested, the oldest page will be uh, 2 is new, 3 is new, 2 has been used, so it's new already. So 1 also new, and 7 will be the oldest one. So we need change the 7 become to the 5. So it will be 3125. Okay, now last uh, is the page 1 is requested. So we see the just time we have put 3125. It have 1 already, so we need not no need to change anything already. So it will be sent before that 3125. The process repeats until the entire reference string is processed. So the highlight like this 1, 2, 3, 4, 6, 1, 5, 7, 2, 3, 5. This all called patch file. The highlighted section in the table indicated patch file. Times when the patch have to be loaded into memory because it has not already present. So key takeaway for LRU is ensure efficient memory usage by prioritizing page use reasoning and swapping out oldest one. However, tracking the least reasoning use page requires additional overhead since the system need to be maintained the order in which page are assisted. So, in summary, the LRU algorithm is a practical and commonly used strategy in operating system. When it has some overhead, it strikes a good balance between simplicity and effectiveness, particularly in systems when reselling use paths are likely to be needed again soon. So that is all for our group part. Thank you very much.